Okay, so we have been doing logic, and we are by now pretty well covered with all these logical as well as set theoretical um, rules. Okay, so whenever necessary, just pull them out and use them. Even though, frankly, in my personal experience and in the way it has been, it usually is an afterthought. So you try to prove something, you try to just develop ideas or read the proof, and then you might use the tools of these very explicit and very formal rules of logic or sets in order to verify your conclusions or verify your logic. Okay, so but that's roughly how we're going to be doing it. So we'll keep this at hand. These are rules, and we'll just use them whenever necessary. So because they're very they're not easy to use. So it only comes from experience. One way, of course, is just to make those logical mistakes, and then learn lessons from those mistakes, and you just then gradually these rules will just become part of your thinking. It is a valid way of doing it, and then you don't really need rules because they will just become your part of your essence of how you think about everything, pretty much. Okay, but it's good to state these things and confront these issues early on rather than making mistakes and learning from mistakes. But mistakes will happen anyway. So these rules are here. It is primarily the operations on sets, operations on propositions, and how they interact. Okay, so just it's not a lot really. And we'll be looking at proofs from now on. A lot of proofs in the all the way through the end, and we'll be just writing proofs like this in a very straightforward way. That this is the proofs the way they look like in any book or an article. You probably I don't think you'll ever see proofs written this way. Okay, so. So that's the idea, that we certainly will try to write them in plain English proofs, that is, and we'll only verify them and maybe with the rules of logic. Even though it's possible also that logic sometimes allows us to sort of shake the tree and see maybe other ways. If you're looking for a proof and you don't see it, then maybe some things can be done logically in order to suggest something, a way to pursue the problem. So anyway, so that's the theorem, a very simple theorem. It's if x is divisible by 4, then x is divisible by 2. Okay, so it's if-then statement, it's an implication, and then the statement itself suggests the way we want to prove it, and that we're going from statement A we're getting to statement B. Okay, so this is statement A, this is statement B, and we're getting from A to B in one direction. So sometimes it's certainly more complicated. This is almost one-step procedure. In general, you might have a long path of like implications with some sources that help you to proceed on, and those are at least are either definitions, okay, and we did use the definitions, or they might be theorems. Okay, so once again, A implies B, and we certainly know from the beginning that we're getting at the end less than we had in the beginning. Okay, so we'll talk about that as well. But here's the proof once again. So we did by definition x divisible by 4 when x can be represented as 4m, where m is another integer. And the same definition applies at the end. So that's how I quickly wrote the proof, by applying definition twice and then leaving room for the actual algebra. But certainly the proof is when you read it, or somebody else reads your proof, it has to be in a more logical, like I have on the right over there, linear fashion. Okay, so ultimately you can only read it linearly, and so the proof are also presented linearly, even though it is tempting to have some kind of diagram, it might help, but usually the final product that we produce, if it is a proof, it is a linear, it is a text. Okay, any questions about this proof? So for m turns into for 2n, okay, for m as an integer is turned over here, right here, into 2n, which proves that the function that x is divisible by 2. Okay, so perfectly good proof. There is not much you can do with it, even though it's a matter of taste. Sometimes people change the way things work out. But logically speaking, there we can do things with it that are with the proof and the statement itself. That just for practice. For practice, we want to so we don't have to learn new mathematics. More things about divisibility or anything. So certainly there are so many of them. But let's just take the same same algebra here, and just prove something something related, which is so if we have a statement there, we had a list of things that we can do with statements. In number one, if you have an implication, if then number one on the list is contrapositive. So well, actually, before we get to contrapositive, let's do a contrapositive. So contrapositive. What's the contrapositive here?
If it's not divisible by 2, then it's not divisible by 4.
Right. So if x is not divisible by 2, then x is not divisible by 4. Okay? Negate, turn the implication around. What I want to do, just once again as an exercise, let's restate both of these theorems in terms of sets. I will start with the first one. So the direct, the theorem itself, is once again x is divisible by 4, then it is divisible by 2. So when we talk about an implication, if then, what are we talking about in terms of sets? One is a subset of the other, so that's right. So and then you can actually think of A as a statement, as we did. What you can think of A as a set, as like this. So x is divisible by 2. It's a set, as a set of integers. It is a subset according to the theorem that x is divisible by 4. Vice versa. I'm sorry. This is a 4. Okay, x is divisible by 2. Okay, so that's the same theorem restated in terms of subsets, and you can see the match between the implication and the inclusion. Okay, now the contrapositive. You remember what it corresponds to: reversal of the inclusion and negation of the statement, or the complement. So x. So I'm doing complement now here. There's the complement of x is divisible by 4. Well, they can say x is not divisible by 4. Well, we already did that, but let's write it anyway. Not divisible. Well, let me do it this more explicitly. So x is not divisible by 2. Okay, so that's the same statement as here. Same. Okay, so that's just this is for exercise. We'll certainly try to do it as often as possible. So to remember that it's there we can go back and forth, and whichever is more convenient. Same with the contrapositive. There is a statement there, the contrapositive, the same exact statement there. If you prove the contrapositive, you prove the theorem as well. So even though we have perfectly good proof right there, we will now let's prove the contrapositive. Because why? Well, because we're just practicing. So these are the two statements. There is an implication. And the idea is then to not just prove the contrapositive, which is proving the same statement as we had to begin with, but rather follow the same order. So start with the assumption and maybe follow maybe a long or short sequence of implications and arrive to our conclusion in that direction. So, okay, so we are not going to be recycling this proof then, because this one starts with the assumption that x is divisible by 4, and then it writes to x is divisible by 2. So our assumption now is the opposite, and so the proof will be a little different. Okay, so the proof of the contrapositive will be then, so x is not divisible by 2. Let's try to analyze. It's not really a proof yet, or maybe it is. It depends on how complex it is. So analysis. So once again, x is not divisible by 2. Okay, and we wanted to conclude that x, well, I put a question mark here because it's not proven yet. So x is not divisible by 4. Okay, so let's look at each of these statements and try to make them not negative. So let's just get rid of the negativity. Okay, so not divisible by 2. How else can you say it? Oh, well, what is divisible by 2? We already know what it is. It is represented as a multiple of 2, or rather, we're talking a multiple of 4, multiple of 2. So if divisible by 2 means that it's a multiple of 2. Okay, let's state it once again. Am I analyzing it? We don't want to keep it in the head. So x is not a multiple of 2. Similarly, x is not a multiple of 4. Okay, so all right. So then what is x then? If it is not a multiple of 2, what is it? Can you algebraically think of what it looks like?
Odd.
What?
Odd.
Odd, yes, but can you think of it algebraically? In the generality, odd requires, once again, the definition. I'm afraid we'll have to make a circle and go back to algebra to explain what odd is. But this formula is x is equal to 2m, or 2n over here, okay? And so what is the other possibility? So that's what even numbers look like. What do odd numbers look like? No, they don't have to be prime necessarily. Just odd. How do we present odd numbers algebraically? They're not multiples of 2, but what? Well, you know, we're talking about divisibility, so maybe even to speak of multiples, maybe not the best way to do it. What?
Multiple 2 plus 4?
No, it is all by remainders. So I'm not sure if you've seen any kind of well, yeah, you probably have divisibility of numbers. When there is a divisibility, it's one thing, and when there might not be divisibility, then there is a remainder. Okay, it is when we have divisibility when the remainder is 0. Okay, so the answer is 2n plus 1. Okay, because there is only one possibility for the remainder. So either it is 0 or it is 1 when you divide by 2. And so when it is 1, then there you have a number not divisible by 2. It has to have the form of 2n plus 1. So so does it sound familiar? An odd number is represented 2n plus 1. Okay, so we'll talk about divisibility more, and we're going to prove statements about divisibility in general. But in this particular case, just divisibility by 2, divisibility by 4 is what we're worried about. A complete statement, x is certainly, we assume that x is some given number, but if I write 2n plus 1, what's missing? How do we introduce n? So x has been introduced already, so let's leave it alone for now. But how do I introduce n? Just to be logical, we have to say something. There are only 2 ways to introduce a new number or an entity into the proof. For any or there is, and this one is there is. So x is given, there is an n such that x is equal to n plus 1. Okay? So similarly, what we want to conclude from this is x is not a multiple of 4, and then there is some kind of m. So x is equal to, and now this time we did it divide by 4, so there are actually 4 possibilities. So when divided by 2, there are 2 possibilities, 0 and 1. When divided by 4, there are 4 possibilities, 0, 1, 2, and 3. Okay, so since it's not divisible by 4, we have x equal to, for some m, 4m plus 1, or 4m plus 2, or 4m plus 3. Okay, so once again, you can rethink of this as union, right? So it's actually union of 3 sets. Okay, so so we need to, from the existence of n on the left, we want to conclude the existence of m on the right. Okay, so any thoughts of how to get there?
Multiply the 2n plus 1 by 2.
Then you're gonna 2n plus 2. You have 2n plus 2, and it is, you cannot multiply x by anything because it's the same x on the left and on the right. So if you multiply, they won't be equal to. What we're talking about is setting this equal to one of these. Okay, so to find m, to find m, we have to set these two, the one on the left and the one on the right, equal to each other and find m. Okay, so, and in fact, how many of these 3 have to be satisfied?
All 3.
No. Or, so one of the 3, if one of the 3 is satisfied, we're okay. So, as a matter of fact, the middle option, look at the middle option, what can you say about it? X is equal to what?
Is it double?
No, x is 2n plus 1 on one hand. On the other hand, x is equal to 4m plus 1. The relation between these two. What? Well, say it again. X, 2n plus 1 is odd, yes. What about 4m plus 2?
That's even.
It is even, so what does it tell you?
Don't use it.
That's right, don't use it. This one is not going to be helpful because there's no way x will be equal to 4m plus 2 because x is assumed to be odd and this one is even. So but which is okay because, like I said, we only need one of these 3 options to be satisfied, and so we're left with 2, which is still fine. Okay, so now just once again keep analyzing, and we'll just set them equal to each other. 2n plus 1 is equal to 4m plus 1. It's the same x, right? So n is given. All we have to do is just n is given. See over here, and we need to find. That's what the difference between there is in the assumption and there is in the conclusion is that it turns a given number into a number that you need to find. Okay, so n is given, and now we need to find m how? Well, you just solve for m, right? So the first possibility is 2n plus 1 is equal to 4m plus 1. What do we do? Then what? What is m? What? 1/2 n. Okay, so what can you say about that? Remember, m, I didn't write it here, but m and n both are integers. So n over 2, m is n over 2, but it might not be an integer. So that's a problem, sort of. Okay, so it might be integer or might be not, depending on whether n is odd or even. Okay, so fortunately we have 2 possibilities. We have 2 possibilities on the right. The second possibility is x is equal to 2n plus 1 is equal to 4m plus 3. Okay, so once again solve it and find m. What is m? Well, just okay. It's really not worth doing it the hard way. So what is it? M is equal to divided by 4, 2n minus, I'm sorry, 2n minus 2, 2n minus 2 divided by 4, right? Yeah? And so, or I could divide by 2, it will be n minus 1 over 2. Once again, there is division by 2, so it's possible that this number is not an integer. Okay? This one might be or might not be an integer, this one too. Okay, so what do we do if you see what we do next? So we split the whole thing into two cases, case 1 and case 2. Okay, so what is case 1? Well, under what circumstances case 1 works? We were supposed to find m, which is an integer. Okay, remember that notation for the integers? So under what circumstances is, in case 1, m an integer?
Even?
If n is even, yes. Okay, what about the case 2? When is m an integer? When n is odd, right? So n minus 1, it's odd, subtract 1, get an even, and so it becomes divisible by 2 and produces an integer. Okay? So in other words, when n is even, case 1 works. When n is odd, case 2 works. So what's the conclusion?
Use case 1 or case 2.
Either one or the on works. And they cover all the possibilities. We have only two possibilities. Either n is odd or even. It's an integer, so it's one or the other. So in either case, the problem is solved. We can find m. And we are in the, therefore, we got getting from left to right, and we have proven it. Okay? So that analysis certainly works out. All that remains is just to write out the proof based on this analysis. So let's try. Usually it's like this. So I put the two statements on left and right, so to compare them, but really what it's about is, if you want to write it linearly, and we do, go like this. Down on the left, the assumption on the left until we are reaching the point where we can cross the bridge into to the right, and then go backwards to recover the original statement. So let's try it. It's all here. I just need to write it in kind of words as much as possible. So if x is not divisible by 2, then there is an n. Let's write word. There is an integer n such that. Okay, so once again, this logical writing is here, but I could put it in a more like essay-like text. So such that x is equal to 2n plus 1. Okay, so then consider two cases. Okay, case 1, if n is even, then x is equal to, once again, 2n plus 1. Okay, hold on a second. Let's proceed on. Then n is equal to say, 2m, m an integer, right? Then, so that's the case 1. Case 1, I probably, if you want to be careful, you just write, you have to say what case is. The case is n is even. Okay, then you proceed to make conclusions from that statement. So the case is n is even. So from that assumption, we could continue on with n is equal to 2m as an integer. Then x is equal to 2n plus 1 is equal to 4, well, 2m plus 1 is equal to 4m plus 1. So what do I say about x? What? What do we care about? Once again, remember going backwards. I cross to the right, and now I go backwards all the way up. and I'm looking at 4n plus 1, and what do I say about this x?
Equal to 4n plus 1.
It is equal to 4n plus 1, but what is that I really care about? Looking at the theorem itself. It is not divisible by 4, right? So 4n plus 1 is not divisible by 4. Okay, case 2. There are only 2, n is odd. Then I write n is equal to 2m, say minus 1, m an integer. Okay, then x is equal to still 2n plus 1 equal to 2n, I'm sorry, 2, I substitute 2m minus 1 plus 1 is equal to 4m. I ended up with minus, but it doesn't really matter. I could have put minus or plus. Well, let's put plus here, like this, plus 3. Okay? Substitute 4n plus 3, and then, so, conclusion is the same. X is not divisible by 4. Okay, so, what do we say at this moment? The words.
Can you repeat that?
What?
What's the question?
What do we say now? Where are we at this point?
So if x is not divisible by 2, then it's not divisible by 4.
Right, which is our theory.
Yeah,
In other words, we're done. Well, this you might remember this one. QED, we're done. So the proof is completed, and we did it in the way we planned. We did it in the contrapositive way.
What
So
is-
yeah,
What is QED?
quod erat demonstrandum, as we were supposed to show, and now we have. Roughly, that's what it means.
So do you
Goes
wanna-
back to the Greeks. What?
Do you want to start saying that now?
No,
QED?
no. It's different. You can. I prefer to do this just to end the proof. Or in the books, you'll usually see this dead or whatever it's called, tombstone or something like that, also to indicate the end of the proof. But you have to point out so that you're done with the proof. In every textbook you see, even in a calculus textbook, there is some kind of symbol that stands to indicate the proof is finished. Okay, so statement of the theorem, then words proof, word proof. Then you go through it with no, destruction, and then until you're done, and then at the end you say, well, I'm done. That should be. You should know that where you end. The reader should know when you finished. Okay. So yeah.
Okay, so I'm confused on why you had 3 different cases to choose from. Like, why did you
That was analysis.
So how do I know when to do that?
Well, it's better. You probably it depends on how difficult the proof is. So if it's difficult enough, you probably start with analysis and just lay out things in front of you, definitions, maybe do some algebra, and then once you have a general idea, start writing the proof. That's what we did. Since I was like I said, I was laying out the proofs, lay out the definitions, and so that's why on the right we are saying that it is not divisible by 4. There are 3 ways of not being not divisible by 4, and one of them was simply irrelevant. But that's to be expected because of we're going to find out next. Because that cannot happen. X cannot be equal to 4n plus 2, so that case was irrelevant, and that becomes relevant in the next. Well, that issue becomes crucial, and the next step is what else do we do with what else do we do with implications? We also consider the contrapositive and converse, right? So let's state the converse. So the statement original was divisible by 4, then it's divisible by 2.
If it's divisible by 2, then it's divisible by 4.
X is divisible by 2, then X is divisible by 4. Okay. So,
What was the contrapositive?
what?
What was the contrapositive? It was.
This is the no, the contrapositive was all the negation, not divisible by 4, then divisible, not divisible by 2. Not vice versa.
If it's not divisible by 2, then it's not divisible by 4.
Right.
Contrapositive.
Right. Hold on a second. Okay. I did state it. Here it is at the very top here. X is not divisible by 2, then it's not divisible by 4. So we are not saying that, right? The contrapositive, once again, even though the proof was very different, we are proving the exact same thing.
So the original would be X is divisible by 4.
Then it is divisible by 2. Right. So that's we started with. That's what we did yesterday. We had a very, very nice proof right here. And then for some reason, I mean, when you have a proof, why are you doing another proof, really? I mean, it's actually, in mathematics is a common pursuit of finding the best proof you can, but this one, and the most beautiful, most short, compact, and maybe insightful as well. But this was a perfectly good proof, so there was no reason other than just to find another one, other than to try for practice. But it is happens sometimes you cannot find a direct proof. What do? Try contrapositive. Okay, so to state your theorem in the contrapositive form and try to follow that direction rather than you might find it, I don't understand the divisibility, for example, here, hypothetically, and then I don't want to speak in terms of divisibility, but rather how maybe I understand non-divisibility, and then I do the contrapositive, and then I discover this proof, which actually turned out to be kind of more complicated, wouldn't you say so? This is more complicated. Okay, so let's do the convert, yeah?
Converse is false, though, right? So can you...
Okay, so it is false, yes. It is indeed false. So what do you do when you want to say it, but you still, how do you prove it? You still have to prove that it's false. How do you prove that it's false? We have proven that theory that it was true.
Number that is divisible by 2 but not by 4.
Right, so prove it's false. It's false. How? Find x such that both of the conditions are satisfied. I'm sorry, one of the assumption condition satisfied, divisible by 2, but not divisible by 2. Such that first, x is divisible by 2, not divisible by 4. Well, certainly, find one, find not just x, 1. All you need to find one single value of x, and the proof is done.
2.
2 is good. So it is called a counterexample. So it's really not technically a proof because there is nothing that there's no implication, there is no beginning or the end of the proof. Well, all you have to do is to offer one single value of x that does not satisfy the theorem. So it satisfies the hypothesis of the theorem, but does not satisfy the conclusion. Okay, that's divisible by 2, not divisible by 4. It is still worthwhile to look at this, and what about sets? How do we interpret this in terms of sets? Okay, so yeah, the conclusion itself, the converse itself, which was turned out to be false. Once again, it is an implication, so it can be stated in terms of sets. So what is it?
All numbers divisible by 2.
X divisible by 2.
The subset, or
Subset, yes. X divisible by 4. Right?
no. Thought X divisible by 4 would be a subset of X.
No, but I'm restating this false theorem.
What the false theorem
Right.
is.
I'm stating it, and now we ask ourselves, what is the, how do we disprove it?
Yeah, okay.
How do we disprove that this
Well,
set?
there's stuff that lies in the divisible by 2 that doesn't lie in divisible by
Right.
4.
Exactly. So you can have an illustration like this. So this theorem says this, A inside of B, and to disprove it, so that's a false theorem, but to disprove it, you need to indicate, you need to show this.
That is the other way, yeah.
Not the other way, no.
Okay.
No, it is sticking out. At the very least, it's sticking out. You don't even know where A is. All you know, all you know is one single value of x. One single value of x you can find, which is in A, but not in B, you're done. So this is B, this is A, and you are showing that there is one element. You don't know anything else about A. All you show that there is one little value there lying. Why are you fucking doing this? Lying outside. So that is our x. This is the counterexample. So every implication statement about sets, about propositions, when you do negation, counterpositive, all of them have counterparts with sets, and so sometimes it's very explicit. So this is when we're talking about numbers and some properties of numbers interacting with each other. Well, you can say that you use those properties to define sets, and then your statement becomes a statement about sets, inclusions of sets, intersections of sets, unions. Yes.
What would be an example of a converse that is true?
Okay, well, that just going to be next. Let me see if I'm finished here. Yes. Okay, so converse is true. Well, theorem. If x is divisible by 6, then what? X is divisible by what?
By 6.
That's true. And that is equivalent, by the way. So it's called a tautology. By the way, there's a good word to use. A tautology, 1 is equal to 1, and so on, like statements like that. So they're definitely true to begin with, and then they sort of don't have any substance in it. Everything turns into tautology once it's proven. Okay, so if x is divisible by 6, then it's divisible by 2. Okay, is the converse true?
No.
Okay, so how do we make it? So what should I add here in order to make it 2 and 3? So if now, and then you can say that's a theorem, but then you can say it, and conversely, or if you want to keep it short, just say, and vice versa. Okay, so if x is divisible by 6, then it's divisible by 2 and by 3, or backwards. If it's divisible by 2 and 3, then it's divisible by 6. Okay, so once again, let's shake this a little bit, and so in terms of sets, so divisible by 6 is so x is divisible by 6. This set, on one hand. On the other hand, I have two sets on the right. X divisible by 2. X divisible by 3. Okay, so what are the connections between these two? These are the three.
2 and 3 are the factors of 6.
No, I have 3 sets now, and I have my theorem stated right here. What's the relation between these 3 sets?
There's a subset between 6 and the rest of it.
So what symbol do I put here?
Right there, that's an and, so it would be an intersection.
Intersection, right? Okay, and what do I put here?
Subset.
Subset. What about this part?
Just
The theorem has 2 parts now.
flip it.
Flip it, or do I do this?
Gets both ways.
By both ways. So in other words, what does it mean?
They're equal.
They're equal, right? So if you then that's what if a theorem of this nature is turns into. Either you have, well, let me keep it. So these are 2 theorems. In fact, let me put it this way: part A, part B. It is 2 separate theorems. We know that the second part might not be true when the first is. So they're proven most of the time entirely separately. So, and then I state these 2 once again separately. This will be A, right? And this would be B. right? So two separate theorems, but if I want to put them together, let's try to put them together. Let's put it together. How do you put it in one statement? X is divisible by 6, not then, is divisible by 2 and by 3. We say if and only if. Over here, I didn't have enough room here, so I have to write it. If and only if. That's what if and only if means. You don't have to really think about these words exactly what they mean normally, but if and only if means this. It goes both ways. It means that the two statements are equivalent, and it is a shorter way of stating that two-part theorem. You state it as a one-part theorem if you prepare to use if and only if. Okay, yeah?
And the second part, would you just put an equal sign for that?
I would, yes, I would. So, yeah, so let me do that indeed. So, say x, 6 divides x. Let me just write this shortened version. X, 2 divides x. Intersection x, 3 divides x. Okay, so that's the same. Okay, so usually the proving, two proofs, two separate theorems, so usually, not always, usually two proofs. If you have if and only if statements, it is in fact two statements in one. There is no guarantee that both of them are true, so their proofs are separate. The exceptions are, I just want to give an exception of sometimes that you could prove if and only if in a matter of, with the one single proof. How about, it's like in algebra, say 2x plus 1 is equal to 3. I go on and I say 2x is equal to 3 minus 1 is equal to 4. 2x is equal to 4 over 2, x is equal to 2. Okay, so that's algebra like from middle school. Okay, so, but these are statements. What's the relation between the statements? What? They are equivalent, so I could just write it like this. That's what in middle school they don't tell you, but now you certainly should think in these terms very much so. When you're solving equations, then always ask yourself, do I say then, or do I say if and only if? So do I proceed in this fashion? So this is x squared is equal to 1, and then I say x equal to 1. That one goes one way. That's another separate example altogether. So x squared plus 1 is equal to 1. Then you proceed in one direction. Then you cannot reverse. Two statements, not equivalent. Even though you draw a legitimate conclusion, but you did not create an equivalent statement. But if it is an equation simple like that, you can actually proceed from left to right or right to left, and they are equally moving back and forth. So the point is that this you can also, if I take once again that sequence of proof, I could think of this as a proof. I could think of this sequence of statement as a proof of what? From the beginning to the end. So I could say it as a theorem. So it is an interesting exercise also. Take a proof and then say what is that we have proven. So can you say what we have proven here? If I call that computation a proof, what have we proven? What? X is not necessarily equal to 2. So that's, what is the theorem?
Which one are we looking at?
The proof is here. That's the proof I'm talking about. And now I'm doing things backwards. So I have a proof. I now want to say what's the proof of. That's right, yes. 2x plus 1 is equal to 3, if and only if. X is equal to 2, that's right. Okay, so as you can see, it is an if and only if theorem, and it is proven in one line, meaning every transition you make is an equivalent statement, and so you're proving simultaneously two theorems. You can think about it this way. So if this is like this, then I go like that, right? And then there is the backwards one, like this. So x is equal to 2, and I could still reverse it. And I go backwards, like this. Okay, so two proofs for the price of one. It is possible, but no, not common. That's usually like even with algebra, it would be slightly complicated. So, for example, here I would have x squared is equal to 1. If I want an equivalent statement, what is the equivalent statement of x squared equal to 1?
This might be just a stupid
Yeah.
detail, but where did you get 3 minus 1 equals 4?
3 minus 1. No, I was solving... oh, shoot. It is stupid. It's just me being stupid. Well, good thing somebody noticed. Okay, so it is 2, and then it is 2 over 2 is 1. Okay.
All right, thanks.
Thank you.
I was really bugged. I didn't know what that was.
Well, you should be more assertive. Well, you are more assertive than probably somebody else noticed and also didn't say. Is this a problem? You got to point it out. Anyway, so what is the equivalent statement of x squared is equal to 1?
Where are both sides?
X equals plus or minus 1.
It is kind of a sneaky way, the way that using plus or minus 1. I want it more logical, and so I just put and. Okay, just as an example. Okay, so once again, this is the difference of how you proceed. In one direction, how you can proceed in two directions at the same time.
Could you put the absolute value of 1 or no?
You could. Once again, these are the algebraic tools that makes your life easier, and you don't have to write more stuff. So algebra is a way to abbreviate your logic, I suppose. That's what we're talking about here. So it's all of those are good. Yeah, plus or minus 1, absolute value equal to 1. It's all good. This is just an illustration of the logic. So then this needs to be proven. Then, as you can see, the theorem itself. So x is divisible by 6, x is divisible by 2. So it's always, even though I said it is usually two proofs usually. I did say that, but it is always at least worthwhile an effort to try to arrange your proofs in such a way that you can go both ways along the same lines, because after all, we're talking about the same numbers, and we are talking about the two statements that are about the same thing. So inevitably there will be some recycling of the proofs. So for example, divisibility will appear in the whether you go that way or backwards. Converse, they will both include some information about the divisibility definition of divisibility. Okay, and you just have to be careful. So, well, I guess we're out of time. We'll give it a try next week.